Picture this. You're peacefully orbiting the sun, minding your own cosmic business, when suddenly an object tears through your solar system at nearly 40 miles per second. Not only is it moving faster than anything should be moving if it belongs here, but its trajectory seems almost deliberately planned, skimming close to multiple planets with mathematical precision that defies coincidence. Most astronomers would call this a comet. Harvard's Avi Loeb calls it something else entirely: potential alien technology. Welcome to another deep dive where we explore the fascinating intersection of rigorous science and extraordinary possibilities. Tonight we're venturing into one of the most controversial debates currently dividing the astronomical community, centered around a mysterious visitor that's captured headlines and sparked heated academic arguments across the globe. Now, before we begin our journey through hypervelocity trajectories and statistical anomalies, I'd love to know where you're watching from tonight and what draws you to these cosmic mysteries. Are you someone who looks up at the stars and wonders if we're truly alone? Or perhaps you're fascinated by the scientific process itself, watching how researchers grapple with data that doesn't quite fit our expectations. If you find yourself intrigued by these questions about our place in the universe, or if you simply enjoy thoughtful explorations of cutting-edge science, I'd be grateful if you'd consider liking this video and subscribing to join our community of curious minds. It helps more people discover these conversations about the profound questions that shape our understanding of reality. I should mention that tonight's exploration might leave you with more questions than answers. But sometimes the most important conversations begin exactly there, in the space between what we know and what we dare to consider possible. So, settle in, let your thoughts drift beyond the familiar, and join me as we examine a theory that's either groundbreaking science or elaborate speculation, depending on whom you ask. Because somewhere between rigorous mathematics and bold imagination lies the story of 3I/Atlas, an object that's forcing us to reconsider everything we thought we knew about visitors from the stars. The story begins on a summer night in Chile, where robotic telescopes scan the heavens with mechanical precision, searching for threats that might one day endanger our world. The Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS, operates with the single-minded purpose of finding dangerous near-Earth asteroids before they find us. These automated sentinels sweep the entire observable sky multiple times each night, cataloguing the movement of countless celestial objects with mathematical certainty. On July 1st, 2025, one of these telescopes detected something extraordinary. Moving against the star field at tremendous speed was an object unlike anything in our solar system's family portrait. Initially designated with the rather unglamorous identifier A11PL3Z, this cosmic wanderer would soon earn a more formal designation, 3I/Atlas, marking it as only the third confirmed interstellar object in human history. Think about that for a moment. In all our centuries of stargazing, in all our decades of sophisticated astronomical surveys, we've confirmed the existence of exactly 3 objects that definitely originated beyond our solar system's boundaries. The first was ʻOumuamua in 2017, a cigar-shaped enigma that sparked its own controversies. The second was 2I/Borisov in 2019, which behaved more like the comets we expected to find. And now we have 3I/Atlas, an object that's rewriting the rulebook once again. When astronomers first calculated the trajectory of this newcomer, the numbers told a remarkable story. Here was an object travelling at roughly 60 kilometers per second relative to the Sun, moving more than twice as fast as either of its interstellar predecessors. To put that speed in perspective, if you could somehow board a vehicle moving that fast, you could travel from New York to Los Angeles in about 2 minutes. The object was clearly following what astronomers call a hyperbolic trajectory, meaning it's moving far too fast to be captured by our Sun's gravitational embrace. This is a cosmic hit and run, a visitor that will swing through our neighbourhood once and then disappear forever into the vast darkness between stars. But speed alone doesn't make 3i/Atlas controversial. What caught the attention of researchers worldwide was the peculiar precision of its path. Most objects arriving from interstellar space would be expected to approach from random directions, reflecting the chaotic nature of their ejection from distant stellar systems. Instead, 3i/Atlas is travelling on a trajectory that lies within just 5 degrees of our solar system's ecliptic plane, the imaginary disk that contains the orbits of all our planets. This alignment might seem like a minor technical detail, but in the world of orbital mechanics, such coincidences carry profound statistical weight. The probability of a randomly oriented interstellar object happening to align so closely with our planetary disk is approximately 0.2%. In other words, if you launched 1,000 objects randomly from interstellar space, you'd expect only 2 of them to arrive with such precise alignment. Even more intriguing are the close approaches that 3i/Atlas will make to multiple planets during its brief visit. Current calculations show that this object will pass remarkably close to Venus, Mars, and Jupiter, with a cumulative probability of roughly 0.005% for such a series of encounters. These aren't just casual flybys. They represent precisely the kind of gravitational assists that human mission planners use to accelerate spacecraft toward distant targets. Size estimates for 3i/Atlas present another puzzle that defies easy explanation. Based on its brightness and assumed reflectivity, some researchers calculate that this object spans roughly 20 kilometers in diameter, making it substantially larger than ʻOumuamua, which measured only a few hundred meters across. Here's where the statistics become truly perplexing. If interstellar objects follow the same size distribution we observe among asteroids in our own solar system, we should have detected roughly 1 million objects the size of ʻOumuamua before encountering a single object as large as 3i/Atlas. Yet we haven't. In fact, our catalogue of confirmed interstellar visitors remains stubbornly small, consisting of exactly 3 objects spanning a surprising range of sizes and characteristics. Either we've been extraordinarily unlucky in our sampling of the interstellar population, or something about these objects doesn't conform to our expectations. The apparent lack of typical cometary features adds another layer of mystery to 3i/Atlas. When astronomers point their spectrographs at most comets, they detect the characteristic signatures of sublimating gases, water vapor, carbon monoxide, and other compounds that create the glowing coma and streaming tails we associate with these icy visitors. Initial spectroscopic observations of 3i/Atlas showed no such features, revealing only a reddening of reflected sunlight that could originate from the object's surface, rather than from outgassing activity. This absence of cometary signatures struck some researchers as odd, particularly given that the object should be experiencing significant heating as it approaches our Sun. Most comets begin outgassing well before reaching the inner solar system, creating the fuzzy appearance that makes them unmistakable even in amateur telescopes. If 3i/Atlas truly lacks these features, it would represent a fundamentally different type of object, one that somehow resists the solar heating that transforms typical comets into spectacular celestial displays. It's against this backdrop of statistical anomalies and observational puzzles that Harvard astrophysicist Avi Loeb has proposed his most controversial theory yet. In a recent academic paper co-authored with colleagues from the Initiative for Interstellar Studies, Loeb suggests that 3i/Atlas might not be a natural object at all. Instead, he argues the mathematical precision of its trajectory and the apparent absence of cometary features could indicate that we're observing an artificial construct, a piece of extraterrestrial technology, rather than a chunk of primordial ice and rock. This isn't the first time Loeb has suggested that an interstellar visitor might be artificial. His previous work on ʻOumuamua, where he proposed that the object could be a light sail from an alien civilization, established him as the most prominent academic advocate for seriously considering technological explanations for anomalous astronomical observations. That earlier controversy divided the scientific community and sparked intense debates about the boundaries between rigorous hypothesis testing and speculative theorizing. Now, with 3i/Atlas, Loeb is doubling down on his approach, applying the same methodical analysis that made his ʻOumuamua hypothesis simultaneously compelling and controversial. His new paper doesn't simply assert that the object is alien technology. Instead, it carefully examines the statistical improbabilities and behavioral anomalies that might support such an interpretation, while acknowledging the speculative nature of the hypothesis. The paper's title poses the question directly: is the interstellar object 3i/Atlas alien technology? But rather than answering with certainty, Loeb and his colleagues present their analysis as what they call a pedagogical exercise, a thought experiment designed to explore the implications of taking the technological hypothesis seriously. They explicitly state that they don't necessarily believe their own speculation, but they argue that the anomalies surrounding 3i/Atlas warrant careful consideration of possibilities that might otherwise be dismissed out of hand. This careful framing reflects Loeb's broader philosophy about scientific methodology and the role of speculation in advancing knowledge. He argues that dismissing technological explanations before examining the evidence represents a failure of scientific imagination, a kind of intellectual conservatism that could blind us to genuinely revolutionary discoveries. In his view, the scientific community's reluctance to seriously consider extraterrestrial explanations for anomalous observations reflects cultural bias rather than rigorous skepticism. The implications of Loeb's hypothesis extend far beyond academic debates about orbital mechanics and statistical probabilities. If 3i/Atlas truly represents alien technology, its trajectory and timing could provide insights into the intentions and capabilities of its creators. The object's near alignment with our ecliptic plane, for instance, would offer significant advantages to any intelligence seeking to observe or interact with our planetary system, while minimizing the risk of detection. Perhaps most ominously, Loeb's analysis includes speculation about the object's potential connection to what science fiction author Liu Cixin called the dark forest hypothesis. This concept, popularized in Liu's acclaimed novel series, suggests that the universe might be filled with intelligent civilizations that remain silent and hidden to avoid mutual destruction. In this scenario, any civilization that reveals itself becomes vulnerable to attack from more advanced species, creating a cosmic environment of perpetual paranoia and preemptive strikes. If the dark forest hypothesis accurately describes the galactic community, then 3i/Atlas might represent something far more sinister than a scientific curiosity. Rather than a peaceful probe or accidental debris, it could be a reconnaissance mission, gathering intelligence about our world and our capabilities before some larger plan unfolds. The object's trajectory, which will carry it past multiple planets before disappearing behind the Sun at its closest approach, would provide excellent opportunities for such surveillance while remaining largely hidden from Earth-based observations. These speculations venture far into the realm of science fiction, but Loeb argues that they deserve consideration precisely because we lack sufficient data to rule them out definitively. The universe, he points out, is under no obligation to conform to our expectations or comfort levels. If we truly want to understand our cosmic environment, we must be willing to consider possibilities that challenge our assumptions about the nature of intelligence, technology, and interstellar travel. The controversy surrounding Loeb's 3i/Atlas hypothesis reflects deeper tensions within the astronomical community about the proper balance between skepticism and openness to revolutionary ideas. Critics argue that Loeb's approach sensationalizes routine astronomical discoveries, generating media attention that distracts from the careful observational work needed to understand these objects. They contend that extraordinary claims require extraordinary evidence, and that the statistical anomalies surrounding 3i/Atlas, while intriguing, fall far short of proving artificial origin. Supporters of Loeb's work counter that the history of science is filled with discoveries that initially seemed impossible or absurd, from continental drift to quantum mechanics to black holes. They argue that dismissing technological explanations without thorough investigation represents exactly the kind of intellectual rigidity that has hindered scientific progress throughout history. In their view, the astronomical community's hostile reaction to Loeb's theories reflects institutional conservatism rather than genuine scientific rigor. This debate reveals something profound about how we approach the unknown. When faced with observations that don't fit our existing models, do we stretch those models to accommodate the data, or do we question whether our fundamental assumptions might be incomplete? The answer isn't always clear, and reasonable scientists can disagree about where to draw the line between healthy skepticism and premature dismissal. Meanwhile, observational evidence continues to accumulate, and it's painting a picture that's both clearer and more complex than initial reports suggested. Multiple telescopes around the world have now captured detailed images of 3I/Atlas, and many of these observations reveal features that Loeb's initial analysis didn't fully account for. Several independent research teams have identified what appears to be a faint coma surrounding the object, that characteristic fuzzy halo that forms when cometary ices sublimate in the solar wind. These cometary features weren't immediately apparent in the earliest observations, partly because 3I/Atlas was still relatively far from the Sun when first detected. As the object has continued its inward journey, however, the evidence for typical cometary behavior has grown stronger. Astronomers have documented the gradual development of what looks like a tail, streams of dust and gas being swept away from the object by solar radiation pressure. The presence of these cometary features directly contradicts one of the key pillars of Loeb's artificial origin hypothesis. If 3I/Atlas were truly a technological artifact, it shouldn't display the kind of outgassing behavior that's characteristic of natural comets. The fact that it does suggest that beneath whatever surface anomalies initially caught researchers' attention lies a core of primordial ice and rock, much like the comets that populate our own solar system's outer reaches. But Loeb remains unconvinced by these observations, arguing that the apparent cometary features could result from observational artifacts rather than genuine outgassing. He points out that 3I/Atlas is moving extremely rapidly across the sky, which can cause image smearing during telescope exposures. What appears to be a coma, or tail, might actually be motion blur, the optical equivalent of a photograph taken with too slow a shutter speed. This disagreement about the interpretation of observational data highlights one of the fundamental challenges in studying interstellar objects. These visitors move so quickly through our solar system that we have only brief windows to study them before they disappear forever into the cosmic dark. Every observation must be carefully planned and executed, and there's rarely time for the kind of extended monitoring campaigns that astronomers use to characterize objects in stable orbits. The technical challenges become even more daunting when you consider the distances involved. Even at its closest approach to Earth, 3I/Atlas will remain hundreds of millions of kilometers away, appearing as little more than a moving point of light in even the most powerful telescopes. Extracting detailed information about its composition, structure, and behavior requires pushing current technology to its absolute limits. Fortunately, the astronomical community has responded to this challenge with unprecedented coordination and resource allocation. The world's premier space telescopes, including the Hubble Space Telescope and the James Webb Space Telescope, have been enlisted to study 3I/Atlas during its brief passage through our neighborhood. These observations, scheduled for various points along the object's trajectory, should provide the highest quality data ever obtained for an interstellar visitor. The James Webb Space Telescope's infrared capabilities are particularly well suited for this investigation. Unlike optical telescopes that rely on reflected sunlight, Webb can detect the thermal radiation emitted by objects themselves, providing insights into their temperature, composition, and internal structure. If 3I/Atlas is indeed a comet, Webb should be able to identify the specific compounds responsible for any outgassing activity, from water vapor to more exotic ices that might have formed in the frigid environment between stars. These upcoming observations represent a crucial test for competing theories about 3I/Atlas. If the object displays the chemical signatures expected of a natural comet, complete with water, carbon dioxide, and other compounds typical of solar system formation processes, it will strongly support the conventional interpretation. If, however, the spectroscopic data reveals unexpected compositions or behaviors, it could lend credence to more exotic explanations. The timing of these observations adds another layer of complexity to the investigation. 3I/Atlas will reach its closest approach to the Sun in late October, when solar heating should trigger maximum cometary activity if the object is indeed natural. But this perihelion passage will occur with the object positioned on the far side of the Sun as viewed from Earth, making detailed observations extremely challenging during the period when the comet should be most active. This orbital geometry strikes Loeb as suspiciously convenient for any intelligence seeking to avoid detailed scrutiny during a critical phase of its mission. If 3I/Atlas were indeed an alien probe, timing its closest solar approach to coincide with a period of reduced observational coverage would represent exactly the kind of tactical planning one might expect from an advanced civilization. Critics dismiss this interpretation as an example of confirmation bias, the tendency to find patterns that support pre-existing beliefs while ignoring more mundane explanations. They point out that orbital mechanics is deterministic, governed by the same gravitational laws that shape the paths of planets and asteroids throughout the galaxy. The fact that 3I/Atlas will be hidden behind the Sun during perihelion reflects the physics of its hyperbolic trajectory, not the intentional planning of alien engineers. Yet, even as the debate rages about interpretation and methodology, both sides agree on the fundamental importance of studying objects like 3I/Atlas. These interstellar visitors represent our only direct samples of material formed around other stars, chemical fossils that preserve information about conditions in distant stellar systems. Every measurement, every spectrum, every photographic pixel contributes to our growing understanding of how planetary systems form and evolve throughout the galaxy. The broader implications extend far beyond academic curiosity. If interstellar objects prove to be common, they could represent a significant hazard to Earth and other planets. An object moving at 60 kilometers per second carries tremendous kinetic energy. Even a relatively small interstellar asteroid could cause devastating damage if it happened to intersect Earth's orbit. Understanding the population and characteristics of these cosmic visitors becomes a matter of planetary defense, not just scientific interest. Conversely, if some interstellar objects do prove to be artificial, the implications for humanity would be profound beyond measure. The confirmation of extraterrestrial technology would instantly transform our understanding of our place in the universe, raising questions about the prevalence of intelligence, the nature of interstellar communication, and the possibilities for contact or conflict with alien civilizations. These considerations lend urgency to current observational efforts and highlight the need for more sophisticated detection and analysis capabilities. The discovery of 3I/Atlas by an automated survey system suggests that many more interstellar objects await detection, as our sky monitoring capabilities continue to improve. The upcoming Vera Rubin Observatory, with its unprecedented ability to survey the entire visible sky every few nights, should dramatically increase the rate of interstellar object discoveries over the coming decade. This anticipated flood of new detections will provide the statistical sample needed to address many of the questions raised by our current tiny catalogue of confirmed interstellar visitors. Are objects like 3I/Atlas genuinely rare? Or have we simply been unlucky in our sampling? Do interstellar objects follow predictable size distributions, or do they represent a fundamentally different population than the asteroids and comets native to our solar system? And perhaps most importantly, will future discoveries support conventional interpretations or continue to challenge our assumptions about what's possible in the vast spaces between stars? The mathematical precision required for 3I/Atlas to execute its current trajectory raises questions that extend far beyond simple gravitational mechanics. Consider the complexity of planning an interstellar journey that would bring an object so close to multiple planets while maintaining perfect alignment with our solar system's ecliptic plane. Such a feat would require not only advanced propulsion technology, but also sophisticated knowledge of our planetary positions, spanning potentially millions of years of travel time. This brings us to one of the most unsettling aspects of Loeb's hypothesis, the implications of timing and intelligence that it suggests. If 3I/Atlas represents alien technology, its creators would need to have possessed detailed knowledge of our solar system's configuration from a time when human civilization was still in its infancy, or perhaps before it existed at all. The object's current trajectory suggests it was aimed at our solar system with surgical precision, accounting for planetary motions and gravitational influences across vast spans of both space and time. The energy requirements for such a mission boggle the mind. Accelerating even a modest spacecraft to 60 kilometers per second would require more energy than humanity has ever produced in its entire history. The fact that 3I/Atlas maintains this tremendous velocity while apparently showing no signs of deceleration suggests either an inexhaustible power source or propulsion technologies that operate on principles we don't yet understand. Loeb's analysis includes calculations showing that if 3I/Atlas were to execute certain maneuvers during its solar passage, it could theoretically intercept Earth's orbit in late November or early December of this year. This isn't a prediction of impact, but rather an illustration of the tactical options available to any intelligence capable of controlling the object's trajectory. The retrograde nature of its orbit, moving opposite to Earth's direction around the Sun, would create a relative velocity of nearly 100 kilometers per second at closest approach, making any conventional intercept mission by human technology essentially impossible. These velocity calculations reveal something profound about our cosmic vulnerability. If 3I/Atlas does represent alien technology, we are essentially helpless to respond in any meaningful way. Our fastest rockets achieve only a fraction of the speeds necessary to rendezvous with such an object, leaving us in the position of passive observers watching as it executes whatever mission it might have been designed for. The dark forest implications that Loeb raises add a chilling dimension to this helplessness. In Liu Cixin's fictional framework, the universe operates under a kind of cosmic paranoia, where civilizations remain hidden to avoid attracting the attention of more advanced species. The theory suggests that any civilization revealing its location faces eventual destruction by competitors seeking to eliminate potential threats before they can become dangerous. If this dark forest scenario accurately describes galactic politics, then 3I/Atlas might represent the kind of reconnaissance mission that precedes more decisive action. Its trajectory allows for comprehensive observation of our planetary system, while maintaining a sufficient distance to avoid detailed detection. The object could be cataloguing our technological capabilities, assessing our defensive readiness, or simply confirming our existence before reporting back to its creators. The psychological impact of such possibilities extends far beyond academic debates about orbital mechanics. The mere suggestion that we might be under surveillance by alien intelligences forces us to confront fundamental questions about human significance and cosmic isolation. Are we alone in the universe, or are we simply unaware of the vast community of intelligence that surrounds us? And if we're not alone, are our cosmic neighbours benevolent explorers or potential threats operating under the ruthless logic of interstellar competition? These questions become particularly acute when we consider the technological implications of Loeb's hypothesis. Any civilization capable of sending reconnaissance probes across interstellar distances would necessarily possess capabilities far exceeding our own. They would have mastered energy sources, propulsion systems, and material science at levels we can barely imagine. From their perspective, human civilization might appear as primitive as an ant colony appears to us, significant only insofar as it might eventually pose a threat or offer resources worth exploiting. The timing of 3I/Atlas's visit also raises uncomfortable questions about cosmic coincidence. Why now, at this particular moment in human history, when we've finally developed the technological capability to detect and study interstellar visitors? Are we witnessing the beginning of a new era of contact, or simply the latest episode in a surveillance program that has been monitoring our development for centuries? Some researchers have noted that all 3 confirmed interstellar objects have been discovered within the past 8 years, coinciding with dramatic improvements in our sky survey capabilities. This correlation might simply reflect our growing ability to detect these cosmic visitors, but it could also suggest that the frequency of interstellar traffic has increased recently. If the latter interpretation proves correct, it raises obvious questions about what might be driving this apparent surge in activity. The technological challenges of studying 3I/Atlas highlight our continued limitations in investigating objects that refuse to conform to our expectations. Traditional astronomical techniques rely on extended observation periods, allowing researchers to build detailed pictures of celestial objects through patient accumulation of data. Interstellar visitors, however, provide only brief windows of opportunity, flashing through our neighborhood too quickly for comprehensive analysis. This observational challenge becomes even more acute when we consider the specific characteristics that make 3I/Atlas potentially interesting. If the object is indeed artificial, it might be designed to minimize its observational signature, revealing as little as possible about its true nature and purpose. Advanced stealth technologies could make it appear comet-like to casual observation, while concealing more sophisticated internal structures from detailed scrutiny. The upcoming James Webb Space Telescope observations represent our best hope for piercing any such deception. Webb's unprecedented sensitivity and resolution should reveal details about 3I/Atlas that remain invisible to current ground-based telescopes. If the object contains artificial materials or exhibits behaviors inconsistent with natural comets, Webb should be able to detect these anomalies. However, even Webb's capabilities have limits when applied to rapidly moving targets at enormous distances. The telescope's instruments are optimized for studying stationary objects over extended periods, not for tracking fast-moving visitors during brief passages through our solar system. The technical challenges of pointing, tracking, and maintaining focus on 3I/Atlas will push the telescope systems to their operational limits. The international coordination required for these observations reflects the global significance of resolving questions about 3I/Atlas's nature. Astronomers from around the world have set aside their usual competition and territorial disputes to focus their most powerful instruments on this single target. The collaborative effort represents one of the largest coordinated observational campaigns in astronomical history, involving space-based telescopes, ground-based observatories, and even amateur astronomers contributing data from their backyard setups. This unprecedented level of cooperation highlights how the mere possibility of artificial origin transforms routine astronomical observation into something approaching a species-level priority. The potential confirmation of extraterrestrial technology would represent the most significant discovery in human history, fundamentally altering our understanding of our place in the universe and our future prospects as a cosmic civilization. Yet, even as this observational campaign unfolds, the scientific community remains deeply divided about the wisdom of taking Loeb's speculation seriously. Critics argue that the extraordinary media attention surrounding his theories diverts resources and attention from more conventional research that might ultimately prove more fruitful. They contend that the statistical anomalies surrounding 3I/Atlas, while intriguing, represent the kind of coincidences that inevitably arise when dealing with small sample sizes and complex systems. The criticism extends beyond questions of resource allocation to fundamental concerns about scientific methodology and the proper treatment of speculative hypotheses. Many researchers argue that Loeb's approach undermines the careful, evidence-based process that has made modern astronomy so successful. They worry that sensationalized theories about alien technology will damage public trust in science and make it more difficult to secure funding for legitimate research projects. These methodological concerns reflect deeper philosophical questions about the nature of scientific investigation and the proper balance between skepticism and openness to revolutionary ideas. How much evidence should be required before considering extraordinary explanations for unusual observations? At what point does healthy skepticism become counterproductive conservatism that blinds us to genuine discoveries? The historical precedents offer mixed guidance for resolving these questions. Scientific history is indeed filled with revolutionary discoveries that initially seemed impossible or absurd, from the heliocentric model of the solar system to the existence of black holes. Many of these breakthroughs required researchers to challenge established orthodoxy and consider explanations that their contemporaries dismissed as ridiculous. However, history is also littered with speculative theories that generated enormous excitement before being disproven by better observations and more careful analysis. For every Galileo vindicated by subsequent research, there are dozens of researchers whose bold hypotheses led nowhere. The challenge lies in distinguishing between genuinely revolutionary ideas and mere speculation dressed up in scientific language. The case of 3I/Atlas illustrates this challenge perfectly. Loeb's hypothesis rests on solid mathematical analysis of orbital mechanics and statistical probability, yet it extrapolates from these calculations to conclusions that many colleagues find wildly speculative. The boundary between rigorous analysis and unfounded speculation isn't always clear, particularly when dealing with phenomena that push the limits of our current understanding. Meanwhile, the object itself continues its relentless journey through our solar system, indifferent to the debates raging about its nature and significance. Every day brings new observations and measurements that gradually fill in details about its composition, behavior, and physical characteristics. The accumulating data will eventually resolve questions about its origin, but not necessarily in ways that satisfy either side of the current controversy. The growing evidence for cometary activity presents the most significant challenge to Loeb's artificial origin hypothesis. Multiple independent observations have now documented the development of what appears to be a genuine coma and tail, the characteristic signatures of sublimating ices responding to solar heating. These features become more pronounced as 3I/Atlas approaches its perihelion passage, following exactly the pattern expected for natural comets. Yet Loeb continues to argue that these apparent cometary features might result from observational artifacts or misinterpretation, rather than genuine outgassing. He points to the technical challenges of observing rapidly moving objects and suggests that what appears to be a coma might actually be image smearing caused by the object's tremendous velocity across the sky. Similarly, apparent tail features could result from scattered light or instrumental effects rather than actual streams of cometary debris. This disagreement about the interpretation of observational data reflects one of the fundamental challenges in modern astronomy. As our instruments become more sensitive and our targets more exotic, the line between genuine astronomical phenomena and instrumental artifacts becomes increasingly blurred. Distinguishing between real features and observational noise requires careful analysis and often multiple independent confirmations using different techniques and instruments. The controversy surrounding 3I/Atlas also highlights the changing nature of astronomical discovery in an era of automated sky surveys and social media. Unlike previous generations of astronomers who could conduct their research in relative obscurity, today's researchers find their work subject to immediate public scrutiny and media attention. Preliminary results that might once have been discussed quietly among colleagues now become headlines within hours of publication. This accelerated pace of public engagement brings both benefits and risks. On the positive side, it allows the broader public to participate in scientific discovery and helps maintain support for astronomical research. Citizens around the world are following the 3I/Atlas story with genuine fascination, learning about orbital mechanics, statistical analysis, and the scientific method along the way. However, the media attention also creates pressure for researchers to present their findings in simplified, dramatic terms that may not accurately reflect the uncertainty and complexity inherent in scientific investigation. The nuanced analysis required to properly evaluate competing hypotheses doesn't always translate well into newspaper headlines or social media posts, leading to public misunderstanding about the strength of evidence supporting various theories. The case of 3i/Atlas illustrates these communication challenges perfectly. Media coverage has tended to focus on the most sensational aspects of Loeb's hypothesis, while paying less attention to the careful caveats and limitations he includes in his academic papers. The result is a public perception that the alien technology hypothesis enjoys stronger scientific support than it actually possesses, while the growing evidence for natural origin receives less attention despite its greater empirical foundation. This communication gap between scientific research and public understanding reflects broader challenges facing the scientific community in an era of information overload and declining trust in expertise. How can researchers effectively communicate the uncertainty and complexity of their work while still engaging public interest and support? How can they maintain intellectual honesty about the limitations of their findings while also conveying the excitement and significance of their discoveries? These questions become particularly acute when dealing with topics like potential extraterrestrial technology that capture public imagination in ways that more conventional astronomical research rarely achieves. The enormous public interest in 3i/Atlas creates opportunities for education and outreach, but it also creates risks of misunderstanding and disappointment if the final results don't match public expectations for dramatic revelation. As we await the results of ongoing observational campaigns, the 3i/Atlas controversy serves as a fascinating case study in how modern science grapples with anomalous observations that challenge conventional understanding. Whether the object ultimately proves to be an exotic comet or something more extraordinary, the debates surrounding its investigation reveal important tensions within the scientific community about methodology, speculation, and the proper treatment of revolutionary claims. The resolution of these questions will have implications extending far beyond the specific case of 3i/Atlas. As our detection capabilities continue to improve and more interstellar objects enter our catalogue, we will inevitably encounter additional anomalies and puzzles that test the boundaries of our current understanding. How we handle these challenges will shape the future development of astronomy and our broader approach to investigating the unknown. The statistical foundations of Loeb's argument deserve careful examination, as they form the mathematical backbone supporting his most controversial claims. When we speak of a 0.2% probability for 3i/Atlas's ecliptic alignment, we're not merely discussing abstract numbers, but rather the fundamental question of whether the universe operates according to random chance or deliberate design. Consider what these probabilities actually mean in practical terms. If you were to randomly scatter interstellar objects throughout space, allowing them to approach our solar system from any direction, only 2 out of every 1,000 would arrive with the precise alignment we observe in 3i/Atlas. The odds improve slightly when we account for the gravitational focusing effect of our Sun, which tends to bend incoming trajectories toward the ecliptic plane. But even with this correction, the probability remains remarkably low. The cumulative effect of multiple low-probability events becomes even more striking when we examine the object's planned encounters with Venus, Mars, and Jupiter. Each individual planetary approach might be explained as coincidence, but the combination of all three creates a probability so small that it challenges our intuitive understanding of random events. We're venturing into territory where coincidence begins to strain credulity, where the mathematics themselves seem to whisper suggestions of intention rather than accident. Yet probability alone cannot definitively prove artificial origin, as critics are quick to point out. Low probability events occur constantly throughout the universe. Indeed, they must occur if the universe is to remain interesting and dynamic. The formation of life on Earth, the precise conditions that allow liquid water to exist on our planet's surface, the specific nuclear processes that power stars, all of these phenomena involve chains of unlikely events that nevertheless occurred through natural processes. The challenge lies in determining where to draw the line between intriguing coincidence and compelling evidence. Loeb argues that we should apply the same standards we use in other scientific investigations, where multiple converging lines of evidence can support conclusions even when individual pieces of data remain ambiguous. A detective doesn't require absolute proof to identify a suspect. Rather, they look for patterns and correlations that make one explanation more likely than alternatives. In the case of 3I/Atlas, Loeb sees such a pattern emerging from the combination of trajectory alignment, planetary encounters, unusual size, and apparent lack of typical cometary features. None of these characteristics alone proves artificial origin, but taken together, they create what he considers a compelling case for serious investigation of the technological hypothesis. The size discrepancy presents particularly intriguing puzzles when viewed through the lens of population statistics. Our understanding of interstellar object demographics comes primarily from observations of asteroids and comets within our own solar system, where smaller objects vastly outnumber larger ones. This size distribution follows what astronomers call a power law, where each doubling of diameter corresponds to roughly an 8-fold decrease in frequency. If interstellar objects follow similar patterns, the detection of a 20-kilometer object like 3I/Atlas should be preceded by the discovery of hundreds of thousands of smaller visitors. The fact that our interstellar catalogue remains so sparse suggests either that these objects are far rarer than current models predict, or that something fundamental about our assumptions needs revision. Loeb proposes that artificial objects might follow entirely different size distributions than natural ones. While natural formation processes tend to produce many small fragments for every large body, technological artifacts might cluster around specific sizes optimized for their intended functions. A civilization designing interstellar probes might favor standardized dimensions that balance payload capacity against propulsion requirements, creating a population dominated by objects of similar scale rather than the continuous size spectrum we observe among natural bodies. This hypothesis makes testable predictions about future discoveries. If interstellar visitors are predominantly natural, we should eventually detect many smaller objects as our survey capabilities improve. If some fraction represents alien technology, we might instead observe clustering around preferred sizes, gaps in the size distribution, or other patterns reflecting engineering considerations rather than collision physics. The apparent absence of spectroscopic signatures typical of outgassing comets initially provided strong support for Loeb's technological interpretation. Most comets begin displaying activity well before reaching the inner solar system, as solar heating sublimes surface ices and releases gases that create characteristic absorption and emission lines in their spectra. The fact that early observations of 3I/Atlas showed no such features suggested it might be composed of entirely different materials. However, as we've discussed, subsequent observations have begun to reveal what appears to be genuine cometary activity. The development of a visible coma and the detection of what looks like a tail structure follow the expected timeline for natural comets approaching the Sun. These observations present the most direct challenge to hypotheses invoking artificial origin, as they suggest that beneath any unusual surface characteristics lies a core of primordial ice responding predictably to solar heating. Loeb's response to this emerging evidence demonstrates both the strength and weakness of his approach to anomalous observations. Rather than immediately abandoning his technological hypothesis in light of apparent cometary features, he questions whether these observations truly represent what they appear to show. He points to the technical challenges of imaging rapidly moving objects and suggests that apparent cometary activity might result from instrumental artifacts or misinterpretation of scattered light. This skepticism toward conventional interpretations reflects Loeb's broader philosophy about scientific investigation. He argues that the astronomical community too readily accepts familiar explanations for unusual phenomena, failing to adequately consider alternatives that might challenge existing paradigms. In his view, the appearance of cometary features in 3i/Atlas doesn't necessarily disprove artificial origin. It simply adds another layer of complexity to an already puzzling set of observations. Critics see this approach as fundamentally unscientific, arguing that it represents a form of special pleading where any evidence contrary to a preferred hypothesis gets dismissed or reinterpreted rather than accepted at face value. They contend that genuine scientific investigation requires researchers to modify or abandon theories when confronted with contradictory evidence, rather than finding increasingly elaborate ways to preserve speculative ideas. The debate reflects deeper philosophical differences about the nature of scientific progress and the proper treatment of revolutionary claims. Thomas Kuhn's influential work on scientific revolutions describes how paradigm shifts often require researchers to reconsider fundamental assumptions about the nature of reality. In this framework, Loeb's willingness to question conventional interpretations might represent the kind of intellectual courage necessary for genuine breakthroughs. Alternatively, critics argue that Kuhn's analysis applies primarily to situations where existing paradigms face systematic failures across multiple domains. The observation of cometary features in 3i/Atlas doesn't represent a failure of our understanding of comet behavior. Rather, it confirms that our models work exactly as expected. The object is behaving like a comet because it is a comet, regardless of whatever statistical anomalies might characterize its trajectory. The resolution of this disagreement will likely depend on the quality and interpretation of data from upcoming observations using the James Webb Space Telescope and other advanced instruments. These measurements should provide unprecedented detail about the chemical composition of any gases being released by 3i/Atlas, allowing researchers to determine whether the apparent cometary activity truly represents sublimating water ice and other familiar compounds. If Webb detects the expected signatures of water vapor, carbon dioxide, and organic compounds typical of solar system comets, it will strongly support natural origin, despite any trajectory anomalies. However, if the spectroscopic data reveals unexpected compositions or isotopic ratios that differ significantly from solar system norms, it could breathe new life into more exotic explanations. The isotopic composition of cometary gases provides particularly powerful diagnostic information about their origins. Objects formed in our solar system should display isotopic signatures reflecting the specific conditions present in the early solar nebula 4.5 billion years ago. Comets originating around other stars might show different ratios reflecting the unique chemistry of their parent systems. Even more intriguingly, artificial objects might display isotopic signatures that don't match any natural formation process. Advanced civilizations capable of interstellar travel might use manufacturing techniques that create distinctive chemical fingerprints, allowing us to identify technological artifacts through spectroscopic analysis, even when their external appearance mimics natural phenomena. The possibility of such sophisticated camouflage raises disturbing questions about our ability to recognize alien technology when we encounter it. If extraterrestrial civilizations possess the capability to design probes that perfectly mimic natural comets while conducting reconnaissance missions, how many such visitors might we have already overlooked? Our entire catalogue of supposedly natural interstellar objects might require re-examination through this lens. This concern becomes particularly acute when we consider the limited observational windows available for studying these rapidly moving targets. Most interstellar visitors remain detectable for only a few months before disappearing forever into the cosmic dark. If some of these objects represent alien technology designed to avoid detection, we might be missing crucial opportunities to identify and study them during their brief passages through our neighborhood. The timing implications of Loeb's analysis add another layer of complexity to these considerations. His calculations suggesting that 3i/Atlas could theoretically intercept Earth's orbit in late November create a specific timeline for testing his hypothesis. If the object were indeed under intelligent control, we might expect to observe course corrections or other anomalous behaviors during this critical period. The fact that such maneuvers would require only modest changes in velocity makes them potentially difficult to detect against the background of measurement uncertainties and gravitational perturbations from planetary encounters. Advanced propulsion systems might produce accelerations so small that they remain within the error bars of our current tracking capabilities, while still enabling significant trajectory modifications over time. This observational challenge highlights our continued dependence on ground-based measurements for tracking interstellar objects. While space-based telescopes like Hubble and Webb provide superior image quality and spectroscopic capabilities, the precise astrometric measurements needed to detect subtle course changes rely primarily on Earth-based observatories that must contend with atmospheric distortions and other limitations. The development of more sophisticated tracking networks, including space-based astrometric missions and improved ground-based facilities, represents a crucial investment in our ability to study future interstellar visitors. As the rate of discovery increases with improved survey capabilities, we'll need correspondingly advanced tools for characterizing these objects during their brief appearances. The broader implications of the 3I/Atlas controversy extend far beyond questions about this specific object to fundamental issues about how we search for evidence of extraterrestrial intelligence. Traditional SETI programs focus on detecting radio signals or other electromagnetic emissions that might indicate the presence of technological civilizations. The possibility that alien technology might visit our solar system opens entirely new avenues for investigation. If interstellar probes represent a common exploration strategy for advanced civilizations, our solar system might host a regular parade of such visitors that we've simply failed to recognize. The objects we currently classify as natural comets and asteroids might include a fraction of artificial artifacts, conducting long-term monitoring or resource assessment missions. This possibility transforms routine astronomical observation into a form of archaeological investigation, where careful analysis might reveal evidence of ancient visitations or ongoing surveillance. Every unusual object, every statistical anomaly, every behavior that doesn't quite match theoretical predictions becomes potentially significant as evidence of intelligence rather than mere curiosity. The psychological impact of this expanded search space cannot be underestimated. The realization that we might be surrounded by alien technology masquerading as natural phenomena would fundamentally alter our perception of humanity's place in the universe. We would no longer be cosmic orphans developing in isolation, but rather subjects under observation by intelligences whose capabilities and intentions remain completely opaque. The dark forest implications that Loeb raises make this scenario particularly unsettling. If the galaxy operates according to principles of competitive exclusion, where advanced civilizations eliminate potential rivals before they can become threats, then the presence of monitoring probes might herald more aggressive action. Our growing technological capabilities, particularly our development of space-based industry and interplanetary travel, might trigger responses from civilizations that previously considered us harmless. These speculations venture far into the realm of science fiction, but they reflect genuine strategic considerations that any responsible analysis of potential alien contact must address. If extraterrestrial intelligence exists and possesses the capability for interstellar travel, we cannot assume that their intentions align with our hopes for peaceful cooperation and mutual benefit. The historical record of contact between civilizations at different technological levels offers sobering lessons about the likely outcomes of such encounters. Advanced societies have consistently dominated or displaced less developed ones, often without malicious intent but simply through the inexorable pressure of superior capabilities and resource needs. From a galactic perspective, human civilization might appear as insignificant as an ant colony appears to us, worthy of study but not necessarily of protection if our interests conflict with those of more advanced species. The possibility that 3I/Atlas represents advanced reconnaissance for some larger plan forces us to confront these uncomfortable realities about our cosmic vulnerability. Yet even as we grapple with these existential implications, the scientific process continues its methodical work of observation, analysis, and hypothesis testing. The upcoming James Webb Space Telescope observations will provide our most detailed look yet at 3I/Atlas, potentially resolving questions that have generated such intense debate within the astronomical community. The technical challenges of these observations reflect the cutting-edge nature of the investigation. Webb's instruments were designed primarily for studying stationary targets over extended periods, not for tracking rapidly moving objects during brief passages through our solar system. The telescope's pointing and tracking systems must be pushed to their operational limits to maintain focus on 3I/Atlas as it races across the sky at tremendous velocity. The observational strategy involves carefully timed exposures designed to maximize signal-to-noise ratios while minimizing the blurring effects of the object's rapid motion. Multiple observations using different instruments and wavelength ranges will provide complementary information about composition, temperature, and behavior that no single measurement could capture. The coordination required for these observations extends beyond technical considerations to questions of resource allocation and priority setting within the astronomical community. Telescope time on facilities like Webb represents an extremely valuable and limited resource, with demand far exceeding availability. The decision to dedicate significant observing time to studying 3I/Atlas reflects both the scientific importance of resolving questions about its nature and the broader public interest in understanding our cosmic environment. International cooperation has proven essential for maximizing the scientific return from these observations. Ground-based telescopes around the world are contributing complementary measurements that help fill gaps in space-based coverage and provide independent confirmation of key results. Amateur astronomers are also playing important roles, contributing observations and measurements that supplement professional efforts. This collaborative approach reflects the global significance of resolving questions about 3I/Atlas's nature. The potential confirmation of extraterrestrial technology would affect all of humanity, not just the scientific community, making it appropriate that the investigation involve researchers and resources from around the world. The democratic nature of this collaboration also helps address concerns about the proper treatment of extraordinary claims within the scientific community. By involving multiple independent research groups using different instruments and analysis techniques, the investigation builds in natural checks against bias and error that might affect any single team's conclusions. However, this collaborative approach also creates challenges for communication and coordination, as different groups work with varying levels of resources, expertise, and theoretical preconceptions. Ensuring that all relevant observations receive proper consideration and that conflicting results get resolved through additional measurements rather than ignored requires careful management of the overall research effort. The timeline for resolving these questions adds urgency to current observational campaigns. 3I/Atlas will remain accessible to detailed study for only a few more months before fading into the distance beyond our telescope's reach. Once it disappears, we'll be left to analyze whatever data we've managed to collect, with no opportunity for follow-up observations or additional measurements. This limited window creates pressure to maximize the scientific return from every observation while the object remains within range. Research teams are working around the clock to plan and execute measurements, analyze data, and coordinate their efforts with colleagues around the world. The results of these intensive efforts will ultimately determine whether 3I/Atlas joins the ranks of well-understood natural comets or continues to challenge our assumptions about what's possible in the vast spaces between stars. Either outcome will contribute important knowledge to our growing understanding of interstellar objects and their role in the broader galactic ecosystem. If 3I/Atlas proves to be a natural comet, despite its unusual trajectory, it will provide valuable insights into the formation and evolution of planetary systems around other stars. The chemical composition of its ices will preserve information about conditions in its parent stellar system, offering glimpses into environments that remain far beyond our direct observational reach. Alternatively, if evidence for artificial origin proves compelling, it would represent the most significant discovery in human history, fundamentally altering our understanding of intelligence, technology, and our place in the cosmic community. The implications would extend far beyond astronomy to philosophy, religion, politics, and every other domain of human thought and activity. As we await these crucial observations, the controversy surrounding 3I/Atlas serves as a fascinating case study in how science grapples with phenomena that challenge conventional understanding. The debates reveal important tensions between skepticism and openness to revolutionary ideas, between rigorous methodology and speculative theorizing, between careful analysis and sensational claims. These tensions are not necessarily problems to be solved, but rather creative forces that drive scientific progress by ensuring that extraordinary claims receive the extraordinary scrutiny they deserve, while preventing premature dismissal of genuinely revolutionary discoveries. The resolution of questions surrounding 3I/Atlas will provide important lessons about how the scientific community should handle similar challenges in the future. The stakes of these upcoming observations extend far beyond academic curiosity into questions that touch the very essence of human existence. We find ourselves at a remarkable juncture in our species' development, possessing just enough technological sophistication to detect these cosmic visitors while remaining frustratingly limited in our ability to study them comprehensively. It's rather like being handed a book written in a language we're only beginning to understand, with pages that turn themselves before we can fully decipher their meaning. The international astronomical community's response to 3I/Atlas reveals something profound about how we approach the unknown as a species. When faced with observations that don't fit neatly into our existing frameworks, we see both our greatest strengths and most troubling weaknesses on full display. The collaborative spirit that has united researchers across continents demonstrates humanity at its finest, pooling resources and expertise in pursuit of truth regardless of national boundaries or institutional rivalries. Yet, the heated debates surrounding interpretation of the data also expose our deeply human tendency to defend cherished beliefs even when confronted with contradictory evidence. The astronomical community's polarized reaction to Loeb's hypothesis reflects broader cultural tensions about authority, expertise, and the proper treatment of ideas that challenge established orthodoxy. Perhaps most importantly, the 3I/Atlas controversy forces us to confront fundamental questions about our readiness for contact with extraterrestrial intelligence. If this object does represent alien technology, as Loeb suggests, then we are spectacularly unprepared for the implications. We have no established protocols for confirming such discoveries, no international frameworks for coordinating responses, and no consensus about how to communicate such momentous findings to a global public already struggling with information overload and declining trust in institutions. The timing could hardly be more challenging. Human civilization currently faces numerous existential threats, from climate change to nuclear proliferation to the destabilizing effects of technological disruption on traditional social structures. The confirmation that we are not alone in the universe would add another layer of complexity to an already overwhelming array of challenges, requiring urgent attention and coordinated global response. Yet perhaps this timing is not entirely coincidental. Our growing technological capabilities, particularly in space-based observation and analysis, have reached the threshold necessary for detecting and studying interstellar visitors, just as the frequency of such discoveries appears to be increasing. Whether this correlation reflects improved detection capabilities or genuine changes in interstellar traffic patterns remains an open question with potentially profound implications. The broader context of our search for extraterrestrial intelligence has evolved dramatically since the early days of SETI programs focused primarily on radio signals from distant stars. The possibility that alien technology might visit our solar system regularly, perhaps disguised as natural phenomena, opens entirely new dimensions for investigation. We might be surrounded by evidence of extraterrestrial intelligence that we've simply failed to recognize because it doesn't match our preconceptions about how such evidence should appear. This expanded search space creates both opportunities and challenges for future research. Every unusual astronomical observation becomes potentially significant, requiring more sophisticated analysis and broader consideration of alternative explanations. The statistical tools and theoretical frameworks we use to distinguish between natural and artificial phenomena must evolve to keep pace with our growing catalogue of anomalous observations. The role of artificial intelligence and machine learning in this endeavour cannot be overstated. As the volume of astronomical data continues to grow exponentially, human researchers will increasingly rely on automated systems to identify patterns and anomalies that might indicate artificial origin. These systems must be trained to recognize signatures of technology that we ourselves might not fully understand, a challenging task that pushes the boundaries of current AI capabilities. The educational implications of the 3i/Atlas controversy extend far beyond professional astronomy to fundamental questions about scientific literacy and critical thinking in an increasingly complex world. The public's fascination with the possibility of alien visitation provides unique opportunities for engaging broader audiences in discussions about scientific methodology, statistical analysis, and the difference between speculation and evidence-based conclusions. Yes. However, the media coverage of Loeb's hypothesis also demonstrates the challenges of communicating nuanced scientific arguments in an environment optimized for sensational headlines rather than careful analysis. The gap between technical papers published in academic journals and their representation in popular media creates fertile ground for misunderstanding and misinterpretation. Educational institutions at all levels must grapple with how to prepare students for a world where extraordinary claims about extraterrestrial intelligence might transition from science fiction to established fact. The skills needed to evaluate such claims, from statistical reasoning to understanding of physical principles to appreciation of the scientific process itself, become increasingly important as our technological capabilities expand our ability to detect previously unimaginable phenomena. The philosophical implications of potential alien visitation challenge fundamental assumptions about human uniqueness and cosmic significance that have shaped religious and secular worldviews for millennia. The confirmation that intelligence exists elsewhere in the universe would force a profound re-evaluation of humanity's place in the cosmic order, with implications extending far beyond astronomy to theology, philosophy, and ethics. These considerations become particularly acute when we contemplate the possibility that our cosmic neighbours might not share our values or intentions. The dark forest hypothesis that Loeb invokes suggests a universe where intelligence operates according to principles of competitive exclusion rather than cooperative exploration. In such an environment, our growing technological capabilities might mark us as an emerging threat requiring preemptive action rather than a potential partner worthy of peaceful contact. The strategic implications of these scenarios extend beyond academic speculation to genuine questions of planetary defense and species survival. If advanced extraterrestrial civilizations do exist and possess the capability for interstellar travel, humanity's continued existence might depend on factors entirely beyond our control, or even our understanding. Current efforts to develop space-based industry and expand human presence beyond Earth take on new significance when viewed through this lens. Our growing capabilities in space might either increase our vulnerability by making us more visible to potential threats or enhance our survival prospects by distributing human civilization across multiple worlds. The economic implications of confirmed extraterrestrial intelligence would ripple through every sector of human activity. Financial markets built on assumptions about terrestrial resource scarcity might collapse if alien technology demonstrated the feasibility of asteroid mining or other space-based industries. Traditional concepts of national sovereignty and territorial control might become obsolete in the face of civilizations capable of casual interstellar travel. Yet these same technological revelations might also offer unprecedented opportunities for human advancement. Contact with alien intelligence, even indirect contact through the study of their artifacts, could provide access to scientific and engineering knowledge that would accelerate human development by centuries or millennia. The challenge lies in managing this transition in ways that preserve human autonomy and dignity, while taking advantage of opportunities for advancement. History provides numerous examples of less advanced civilizations being overwhelmed by contact with more sophisticated societies, often leading to cultural collapse and demographic disaster. As we await the results of ongoing observations, the 3I/Atlas controversy serves as a valuable rehearsal for how humanity might respond to more definitive evidence of extraterrestrial intelligence. The debates surrounding Loeb's hypothesis reveal both our strengths and weaknesses in dealing with paradigm-shifting discoveries, providing important lessons about the need for improved international coordination and more sophisticated frameworks for evaluating extraordinary claims. The technical capabilities demonstrated in the coordinated observational campaign also showcase humanity's impressive ability to mobilize resources and expertise when faced with sufficiently compelling challenges. The collaboration between professional astronomers, amateur observers, and advanced space-based facilities represents the kind of coordinated effort that would be essential for responding effectively to confirmed alien contact. Whatever the ultimate resolution of questions surrounding 3I/Atlas, the object has already succeeded in forcing us to confront fundamental questions about our cosmic environment and our preparedness for discoveries that might fundamentally alter human civilization, whether it proves to be an exotic comet or something far more extraordinary. It has served as an invaluable catalyst for discussions about methodology, speculation, and the proper treatment of phenomena that challenge our understanding of what's possible. The coming months will bring unprecedented observations using humanity's most advanced astronomical instruments, providing data that should definitively resolve questions about the object's nature. These measurements will either confirm that we're dealing with a particularly unusual but ultimately natural comet, or they will open doorways to possibilities that have existed only in the realm of science fiction. Either outcome will contribute valuable knowledge to our understanding of interstellar objects and the broader galactic environment. If 3I/Atlas proves natural, it will provide insights into planetary formation processes around distant stars and the mechanisms that eject objects into interstellar space. If it proves artificial, it will represent the beginning of a new chapter in human history, one where we must grapple with evidence that intelligence exists elsewhere in the universe and possesses capabilities far exceeding our own. As we prepare for whatever revelations await, the 3I/Atlas controversy reminds us that the universe remains far stranger and more complex than our current understanding suggests. Whether we're alone in the cosmos or sharing it with intelligences whose intentions remain opaque, our continued survival and prosperity depend on maintaining both rigorous skepticism and openness to possibilities that challenge our deepest assumptions about reality. The night sky that has inspired human wonder for millennia might conceal visitors whose presence would transform our understanding of everything, from physics to philosophy. As we peer deeper into the cosmic dark with ever more sophisticated instruments, we must remain prepared for discoveries that exceed our wildest imagination while maintaining the careful, evidence-based approach that has made modern science so successful. In the end, whether 3I/Atlas represents a chunk of primordial ice or a messenger from the stars, its brief passage through our solar system has already enriched our understanding of both the cosmos and ourselves. It has shown us the power of international scientific collaboration, the importance of remaining open to extraordinary possibilities, and the continued mystery that surrounds our place in the vast, ancient, and perhaps populated universe. So, as you look up at the stars tonight, wherever in the world you might be, remember that somewhere out there, racing away from our sun at incredible speed, a small object continues its eternal journey between the stars. Whether it carries the frozen remnants of a distant world's formation or the technology of an alien civilization, it serves as a reminder that the universe still holds secrets waiting to be discovered by those bold enough to question what they think they know about the nature of reality itself.